Do you know what the definition of a software engineer? Something I heard, it's about it's someone that solves problems you have never knew that you have in a way that you don't understand. A while ago, I was preparing an interview with a candidate, and I was looking for questions. I look for the classic juicy questions, you know, find few, and I left with the 8-queen puzzle. I looked for a solution by myself. I found one, I succeeded, but later I found another one, a better one, and then another one even better, and I don't have to tell you what it did to my ego. And don't worry, I haven't asked this question at the end in the interview. However, in this today, I would like to talk about that subject that it's always better to look for another and better way to do things. And this is what I would like to go through this. I would like to take you through in this presentation through the journey of solving the 8-queen puzzle. I found 5 different solutions, and let's go. Let's start through this journey. My name is Ariel. I'm a chief architect at Applied Materials. Basically, in Applied Materials Israel, we're doing every chip that you, in your phone, in laptop, in your TV, probably go through our metrology and inspection tools that are being developed and even manufactured here in Israel. Technology, and this day Python, are my passion. I actually introduced Python to our R&D here in Israel. As I told you, I found 5 different solutions, and always try to find better and faster way. So let's start. The 8-queen, basically in the 8-queen puzzle, we try to place 8 queens on a chessboard in a way that each queen doesn't threaten the other queen, so they cannot share the same column or the same row or even on diagonals. There is the classic way of the depth first backwards solution, which is about 16 million possibilities, but there are shortcuts. And basically in these shortcuts, we constrain each queen to a single column and a single row. And then what we do, we just running permutation on these options. And we check each permutation only for diagonals, okay? This is the program, basically. We go all the permutation of the above matrix, and if the sum of the diagonals, the sum of all the diagonals are less than, each diagonal is less than 1, we have a solution. There are 92 solutions like this. So basically this here looks how solutions look like. Basically it's array of 0s and 1, and just an example. In this, through this presentation, I'll use the 1 to 64 matrix. It's more clearer than 0 and 1s. It's easy to track the 1 to 64, the examples, and 0 and 1s is a little bit fuzzy. So I will use this one, but every time that you see the 1 to 64, imagine the 0 and 1s. Okay, so let's just jump to the first. There is a trace API in NumPy, which is summarize a single diagonal. Okay, so, and then I'll try to loop all of the diagonals and sum each one of them. In order to loop in all diagonals, I need to rotate the matrix because I need the diagonals in both directions, and we will see the rotation or the flip or whatever, trying to get this matrix, a few ways to do it. So this is one way. which is called rotate. I can rotate the array, and if I rotate it 3 times or -1, I get the matrix, the diagonals in the other direction. So first I I'm running the loop and trace each diagonal. For example, the diagonal 0, trace 0, I trace the main diagonal 1, 10, 19, 29, 36, 46, 55, and 64. And if I trace, for example, trace 6, give me the diagonals of 7 and 16. Okay, so, and they give me the sum of each time diagonals. I'm doing it from top to down. Then I rotate it from left to right, from top to down. Okay, and here everything is all together. Okay, and then I time this. Okay, how long it takes to go over all this 8 factorial, 40,000, you remember? So this takes about 3 seconds. Okay, can I do it faster? So I try to do it faster. I'm trying to use different way, not trace, to, again, loop all the diagonals, but maybe I can sum it myself faster and do it a different way. But before I'm doing this, let's go explain the data structure of NumPy. NumPy array is basically a memory block, okay, with metadata. The display in NumPy, how to read, how to interpret this memory block. So we have the dimension, we have the shape, we have the strides, how to jump lines and how to jump columns, and the pointer to the buffer of data. So if I am taking a different view of this, the same memory data with the same buffer with different memory data, I get if before I got 3 by 3 array, here I get a vector of 9 numbers. Okay? Using this mechanism to just change the metadata, I can get different view of the same array. For example, if I'm using strided, which is a NumPy method, I can just manipulate only the metadata. Okay, just manipulated the metadata. So this strided give me a view, O of 1. Okay, it's not copying, it's nothing. It's just a view of the main diagonal. Okay, for 1 to 61, 19, etc. to 64, main diagonal. If I would like to get, if I will get this strided, I'll get just the view of the numbers 7 to 16. Okay, so as I said, I will loop on all the diagonals. Every time I will call strided and they call sum, okay, because I want this to summarize this. And very similar to trace, I'm looping all over the diagonals from left to right, rotated from top to down, and I'm calling sum, and I'm trying to time it. Okay? Wow. 12 seconds, 13 seconds. Why is that? So looking into it, in this method, I called NumPy 9 times. In the previous one, I called about 5 times. And throwing the loops 30 times, so I'm looping all the diagonals. So I have a factor of calls from Python to NumPy. So if I have many calls to Python to NumPy, I get a performance hit. Okay, so let's try to do it without loop. Okay, without looping, trying to summarize all the diagonals without looping on all the diagonals. Can we do it? Again, before I'm going this, I'm trying to go over 2 other features of NumPy. One of them is broadcasting, if you haven't heard. Basically, NumPy, if we have the array with different shapes during arithmetic operation, NumPy completes the missing dimension. Okay, so all these, the same array, this is 4 by 3, 4 by 3 by 3, and 3 by 3, 3 plus 3 dimension. All these give us the same results, and every time NumPy completes the missing dimension. The advantage of doing it let NumPy to do it, because NumPy is doing it in C, and if I will do it in NumPy, it will take me a long time. The other feature that I would like to talk is fancy indexing. Basically, in NumPy, I can access in one statement multiple elements. Okay, for example, these statements, I assign the main diagonal, 1 to 8 numbers, I assign it in one statement. And again, this one statement is done in C. Okay, or also I'm passing the parameters, but all then it's going to, I can do it, I can basically put NumPy array as the index, another array as the index, and summarize. So in this try, I'm trying to basically turn all the diagonals of the array to rows, because with rows, I have the function sum, and sum I can sum the whole array at once. So I'll try to use sum and turns all the diagonals to lines, to rows. And for this, I need to give a unique number to each diagonal. Okay, so the line number, basically, I will use this unique number as a line number. Okay, so I'm using the broadcasting for this. Okay, so here if I sum this to the range of the arrays, the range of the dimension of the matrix, okay, I can get for a unique number for each diagonal. Okay, so my diagonal gets here the number 7. Using this, so basically what I'm trying to do, I'm trying to create a matrix with zeros. Okay, which the number of all the diagonals, 30 lines of zeros. And then I'm trying to, in one statement, I assign the whole matrix to be lines. Okay, so every diagonal becomes a line in this new matrix. Of course, then I need to rotate it and do it also for the other direction. Okay, so I'm getting a matrix with 30 lines with all the diagonals as lines. Okay, this is, I don't know how you can see, but if you can see it, you can see this is the matrix. And if I call sum on this, I get in one command, in one sum, the summarize of all diagonals. Okay, timing this one is much better. Much better. We got 1.5 seconds for going over all 40,000 plus operation. And why this? Because all the copying probably is done in C, okay? And then we have one command that summarizes also in C, okay? So we have basically very few calls from Python to NumPy. Again, we're trying to do it a different way and in better way, okay? So I try to take the S-trided from the second try, and the padding trick, we're padding with 0 in the last try, and trying to combine them, and basically, again, I will try less doing copying. In the last one, we copy the whole array one by one to the array, so I'll try to do a different copying. Again, I told you that there is different way to rotate, remember, to rotate the array, so here is a different way. And remember, every time it's O of 1. It doesn't copy, it just gives you, it's make with the metadata. So here is flip, or here playing with the index, give us the same, give us the diagonals in the different direction. You see, this is the array, okay? We want this diagonal, and we get it here, okay? After we doing a flip, left, right, or we X with the index and -1, okay? So just you see that in NumPy we can do it in different ways. Now, I'm using this one, and I'm trying to build an array, a stacked array, with 0 paddings, that when I will look on the diagonals, instead of going out of memory, I have a 0 padding when I'm going, for example, on these diagonals, on this 57, okay, you see, it's not running out of the memory, it will have 0 paddings, okay? So I have the 1 to 64, 9 to 63, it will pad with 1, 0, etc. And the 57 will be 157, and then zeros. And then I flip it to get all the diagonals. For example, 1 will get also 0, 0, 0, 0, 1, and then 64, like this, okay? So I flip, so I'm building a stack like this, and then with S-trided, with one command, again, S-trided, O of 1, I get a view of this one, I get a view of this as all the diagonals as rows, okay? And again, it's just a view. Timing this one is 1.10 seconds. It's faster. So probably stacking arrays is a little bit faster than just copying the whole element by element. Both of them done in C. The problem with this one is it doesn't scale well, because now I have an array that's about 4 times bigger than my original array. But you know, sometimes in order to get performance, you use memory. But this is again, this is give us a better performance. Ready for the last try? Okay. The last try, I try to use, we use sum in all the tries from 1 to 4. I use the function sum. I use it in the loop, and then I did it as sum of all the metrics. And I looked for a different way to summarize in NumPy. And I came across the bin count method. Okay, so you remember our indices. We have the indices matrix that every diagonal get a unique number. Okay, and if I run a bin count on this matrix, basically what bin count does, it counts the number of occurrences of a positive number in the matrix, okay? So, for example, the bin count counts, we have 8 times number 7, we have the number 0 1 times, the number 14 1 time, okay? That's what bin count does. How it takes us closer to summarize the diagonals. Bin count has another parameter, which is called weights. What weights does? Weights basically, instead of summarizing and counting the values, it basically sum the elements that correspond in the same of this index. It's in the same of the number of index that we would like to count. It summarizes it. Okay. So, for example, if we would like to count the number 1, okay. If you see, we'd like to count the number 1s. Okay, so instead of doing one occurrence and then second occurrence, it takes the occurrence from 2 and 9 and summarize it. Okay, and if you would like to summarize this diagonal, or we summarize 12 appears 3 times, it goes to the weights and summarizes 14, 8, 55, and 62. Okay, so in this way, we summarize all the diagonals. Of course, again, I will rotate it and summarize again. How long it will take this one? Okay, this one takes less than a second. It's 82 seconds, 0.82 seconds to summarize to find diagonals and summarize for all the 40,000 something options. Okay, and also it's the shortest solution in terms of code. Okay, so remember we started from 3 seconds, we go to 12, and then 1.4, 1.10, and we got less. What I would like to take, it's hard. All the code is in GitHub, so you can go GitHub, search my name, I give the link also, so you will find all the code, you can try it by yourself. But basically what I try to do, that you should take from here, that iteration in Python over NumPy array is basically performance enemy. If you see it, you should try to avoid it. And if you must do it, try to use number or something. But this is when I'm trying to optimize the code, this is the first thing I'm looking for. Is there a loops in the algorithms that loops over the metrics? If you're looking on huge images, you suffer from it. There are almost always multiple ways to solve specific problem in NumPy. Okay, so try to be clever to try to search for another thing. The third thing I'd like to, I hope to tell that if you know the rich API of NumPy, and basically what I did in the beginning, I was just reading the manual, just trying to and play with each method API. And if you learn more APIs, you actually expanding your box of tricks, because I used here tricks. Okay, so you expand them. And the final thing is that if you understand the underlying implementation of you can get performance improvement, because you understand how things work on the beneath, so it's easy to get a performance improvement. And I would like to summarize with John Maxwell's words that search for better things, better ways to do things. Even if you have a solution, sometimes you get a solution, try to search for a better way for two reasons. One, maybe there is you miss something, you missed a better alternative. But even if you started with better alternative, searching for better ways or different ways is just sharpening your skills and creativity and practices. That's all. Okay? So thank you. If you find a better way, you are welcome to email it to me or send it to me or through LinkedIn. I will be happy to edit. You can catch me here on the floor, on the booth. I will be here also tomorrow. And again, thank you for coming and giving me your attention.